Okay, so welcome back. So here's the first question that we are looking at, and this question is based on the topic which is equivalence mechanical system, right? So we have to represent mechanical system uh, in a certain form that is easy, like to simplify or solve. Okay, you want to present the mechanical system to its equivalent form. Okay, so the form which is presented here may not be easy, okay, to solve or to use it for solving the problem. So you have to convert this mechanical system into another form that will be easy, okay. So that is what we call the equivalence of mechanical system. So some questions may ask you to convert it to its electrical equivalence using what we call analogy. Okay, there's a force voltage analogy and force current analogy. But in this problem, we're not looking at that. Okay, so it's just converting mechanical to mechanical. But you have to write in a form in a way that it will be very clear. Okay, for us to solve this problem, you can just apply some basic rules. Okay, some rules like the way we used to those rules we used to apply in electrical circuits. For example, node analysis. That rule, okay, will play a very important role here because we need some knowledge of node analysis there. Okay, so without wasting much of your time, let's get started. Okay, so the question reads, for the spring mass damper system shown below in figure question 1c, M1 and M2 are the masses and are supported by zero friction rollers. Okay, so of these two masses, M1 as well as M2, and those two masses are supported by frictionless. Okay, so there is no friction between the ground and those masses. Okay, so x1 and x2 are their displacements respectively. So the displacement, okay, of mass 1 is x1, or the displacement of mass 2 is x2. Okay, k1, k2 and k3 are the spring constants. So you have three springs here having different constants, k1, k2 and k3. Those are the spring constants. And B is a viscous damping coefficient. Okay, so we have a damper here with a viscous damping coefficient of B. And we have a force F of t which is applied to mass 1. So the force F of t is applied to M1. Okay, and then the first part of the problem says draw the equivalent network. Okay, so we have to draw the equivalent mechanical network of this mechanical system. Okay, and then part 2 says we have to find the transfer function, which is the ratio of the output. So the output you're considering this time is x2, okay, which is the Laplace of x2t. x2s is the output over fs, which is the Laplace of what? F of t. Okay, no x1 of s in the final expression. So this means that we have to solve for x or for x2, and we have to make sure that we get rid of what? X1 completely, not so. Okay, so don't need to have x1. So we have to use substitution or matrix method, whichever method that is capable to solve systems of equations. Okay, so let's start. Now, we are told we have to we have to draw the equivalent network. Okay, so how do you draw the equivalent network if you are given such a system? So the first thing you need to do is to identify the displacements. Okay, you have to identify the displacements in the system. So as you can see, we have two displacements. We have x1 and x2. And then next, you are going to present those displacements as nodes. Okay. Remember, if you remember the electrical system, okay, I mean the electrical circuits, Okay, when you have a node, okay, when you have a node, you used to present that node as a voltage or something, isn't it? You used to find node voltages, node analysis, not so. So this is the same concept we are going to use here. So we're going to present x1, x2 as nodes. So you can think of them like voltage v1 and v2, not so. So I'm going to present these nodes, right? Okay. So here there'll be a node, and here there'll be another node, right? Okay. So this node will be called x1. So you can look at it like a v1 voltage, isn't it? x1 of t. And then this node will be called x2. Okay, sorry. This is x2 of t. Okay, and then so we have two nodes, and then we also need to have another node which we call the reference nodes. Okay, so a reference node can be drawn here, which is just the node, like the way you think of the voltages, the voltage at zero potential, right? Okay, the node is at zero potential, isn't it? So I'm going to draw a reference node here. Okay, so this node here will be reference node here, right? Okay, so this reference is very important always to draw a reference, right? Okay, so that's a reference. Okay, now the next step you need to do is to identify all the elements that are connected to the same displacement, or elements that are having the same displacement, or elements that will be connected to the same node. And those elements that are having the same displacement must be connected in parallel. Okay, so remember that mass number 2 is having displacement what? x2, isn't it? And you notice that the same mass number 2, we have the spring with a spring constant k3. So this means that mass number 2 and the spring are undergoing the same displacement. Okay, so meaning m2 and the spring with a spring constant k3 must be connected in parallel. Okay, so I'm going to connect these two in parallel. Okay, so m2 and the spring with a spring constant k3 will be connected in parallel. Okay, let me just get a mass here. So I'm going to consider this as a mass, and I'm going to consider the color black. Okay, so we have a mass here. Okay, so this mass shall be connected in parallel with a spring. So I'll connect this mass between this node and the ground. Okay, and then in parallel with it, I'm going to connect the spring. Okay, so in parallel to this mass, I'm going to connect the spring. Okay, so this spring here, it has a spring constant K3. Okay, so this is representing a spring for me. And then this mass is M2. Okay, now let's look at node number 1. Node number 1, this mass number 1 undergoes a displacement of x1, right? And the same mass, you can see that there's this spring again attached, isn't it? Okay, so this means that this mass number 1 and the spring must be connected in parallel. And to the same mass as well, you have this force applied, isn't it? So all these elements, the force, the spring, and mass number 1 must all be connected in parallel. Okay, and they are all connected to the same node, which is x1 of t. Okay, so I'm going to draw mass number 2 here, m2. Okay, so this is m2. Okay, and then I'll connect it that way. And also there is a spring, right, in parallel to mass number 2, isn't it? Mass number 1, sorry. There is a spring with a spring constant what? K1, isn't it? And then also there is a force applied here, right? So this applied force. Remember that all the forces that are transmitted through mass number 1, the spring, and the rest of the system are opposing forces. So this force here, I'm going to represent this force just like represent the voltage or current, right? Okay, using this. So in that direction, that force is applied to this system. So it must be in this direction, right? So this force is F of t. And then this is m number 1, or this was supposed to be m2. And then there have a spring here, which is k1. Now, if you go back to the diagram, the next rule is that the elements that are connected between two different displacements must also be connected in parallel, right? Because they're undergoing the same displacement. So there must be connected between those two nodes. Elements that are connected between two displacements must be connected in parallel between those nodes. Okay, so you see that spring number 2, spring k2 and the damper, those guys are having the same displacement, which is between x1 and x2. So they must be connected in parallel between node x1 and node x2. Okay, so I'm going to connect these two elements, which is a spring with a spring constant k2, as well as the damper with a the viscous friction of what? B. Okay, so let me just connect those two in parallel. Okay, so I'm going to draw a line. Okay, it's the same thing. So this is a damper. I'm going to start with a damper. Okay, and then next I can put a spring here, isn't it? Okay. So this damper, it has a viscous friction of B, and the spring has a spring constant of K2. Okay, so now this is a complete equivalent system. Okay, so this is a complete equivalent network, this mass network here. Okay, so that's the end of question number 1. Okay, so part 1, we are done. So this is equivalent. Okay, now we go to part number 2. Let's look at part number 2. What's part number 2 saying? Find the transfer function, which is x2 of s divided by f of s. The Laplace of x2 of t divided by the Laplace of f of s. So for us to do that, since we have two different displacements, we are going to have two different equations. Okay, we're going to have two systems of equation. Okay, we're going to have equation relating to, that would be taken from node number 1, and another equation will be taken from node number 2. Okay, so if you look at node number 1, let's look at the forces that are applied and also the forces that are opposing forces, isn't it? So the applied force here at node number 1 is noticed at just f of t. F of t is applied to node number 1, not so. While the same force now is distributed across what? Through this mass here, through this spring here, through this spring here, and through this damper here. So you can think of like this is a current source, right? This is a current source, isn't it? At this node, and then this current divides. Okay, you have current through this mass number 1. Let's see, this is a resistor, another resistor there, another resistor there. You can think of them like the way you solve electrical circuits, not so. Okay, so this force here must be equal to all these other three forces at this node, right? So f of t must be equal to force through mass number 1, force through the spring k1, force through the spring k2, and force through what? Through the damper. Okay, so let's apply the equation there at node number 1. So I'm going to call this node 1. Okay, so node 1. So I'm saying the applied force f of t equal to all the forces that are opposing, right? So the first force is simply the force through mass number 1. And the force through the mass is simply the force of acceleration, right? According to Newton's law of motion, isn't it? Which is the mass times acceleration. And what is acceleration? Acceleration is simply what? The second derivative of what? Displacement, not so. So which displacement are we considering here? It's this displacement here, okay? Displacement between this mass, right? So remember, this is at x1 of t, this is at 0. So it's more like the voltage between this mass, right? Or this resistor can think of. You see that voltage is simply what? It can be x of t, not so. Okay, so the second derivative of that displacement. So this is it, x1 of t double dash. It's the second derivative, not so. Okay, and then plus another force through the spring here, K1. Okay? Or may just start with a damper. It's okay, but I can start with whichever I want to start with. So this will be K1 times what? The displacement. Remember that the force across the spring is simply the spring constant times its displacement. So the displacement is still x1 of t plus another force through the spring K2. This K2 now I see that the spring is lying between two displacement, not so. So you're going to have the difference. You're going to subtract. Okay, this will be x1 of t minus x2 of t. Okay, plus another force through the damper, and this force is simply b times the derivative of what? The distance. Remember that the force across the damper, okay, which is the viscous friction here, it's the viscous constant or coefficient times what? The derivative of what? Displacement. And those displacement to be what? Those two displacement, right? X1. So we have to find the derivative of this, x1 prime minus x2 prime. Okay, so this is equation with respect to node number one. Now, having found the equation, you have to find the Laplace transform of this also. So the Laplace of f of t simply is f of s, and this is equal to m1, and then the Laplace of second derivative, assuming the initial condition is equal to 0, this is s squared x1 of s plus k1, the Laplace of x1 of s, this x1 of t is simply x1 of s plus k2. Okay, the Laplace of x1 of t, this is x1 of s, and then minus again k2 x2 of s, and then plus, okay, this will be b. The Laplace of the first derivative is simply s, this is x1 of s minus b, similarly s, x2 of s. Okay, and then here I'm going to put all the x1 of s's together and the x2 of s's. So you have this coefficient here, m1 s squared plus, okay, I'm going to get this one here, which is bs, and then plus I'm going to get the coefficient here, which is k1, and then another one is what? It's k2, right? So of k2. The whole of this multiplied by what? x1 of s. And then you see that x2 of s, the negatives, right? So I'm going to factor out the negative. This is minus bs plus k2, isn't it? Okay, from here and that one. K2, and then this is x2 of s. So this is the first equation, okay? This is the first equation if you apply node analysis on node number one, right? Okay, apply node analysis at node number one. It's the first equation you get. And then we also do the same thing to node number two. And now, if you notice, for node number two, there's no applied force here, okay? There's no applied force. All these forces at node number two are simply opposing forces. So the sum of all these forces must be equal to the applied force. But there's no applied force at this node number two. So the sum of all these four forces must be equal to 0, okay? So I'm going to add all these forces at node number two and equate the result to 0. There's no applied force there, okay? So we do the same thing. So how many forces are there? There are four forces across M2, K3, K2, and B, right? Okay. So all these forces must be outgoing forces, of course. So you have a force in this direction, you have a force in that direction, you have a force in this direction, and you have a force in this direction, right? So I'm going to start with it, the force across the mass M2. So this will be, this is node 2, right? That will be m2 times the second derivative of displacement. Which displacement that? The displacement we're looking at is what? The x2, right? And then plus another force through the damper. Okay, the damper is B, right? What distance? Now remember that force is coming from x2 going to x1, right? So this is x2 minus x1. Okay, and then the force across the spring, K2. So this again, K2 would be x2 minus x1, right? And then finally the force across the other spring, K3, times what distance? Displacement is simple what? X2, isn't it? Okay, times x2. and this is equal to 0. Okay, and then also take the Laplace of this. This is m2. Okay, this is m2s squared times x2 of s plus this is bs x2 of s. This is a derivative, sorry, these are derivatives, right? B times c, the derivatives. Okay, minus bs x1 of s plus k2 x2 of s minus k2 x1 of s plus k3 x2 of s. This is equal to 0. And then you can also arrange the x1s and x2s. Okay, so the x1 is this guy here. And also where else can I find x1 here? So it's negative, so I'm going to factor out negative here. This is minus bs plus k2, right? And then plus ms squared. So this is m2s squared plus bs. These are k2s. And then plus k2 plus k3, right? Okay, this is the x2 of s. And they equal to 0. Now, this is a second equation. Now remember that we're interested in x2, so I have to get rid of x1. Oh, of course, here I have to multiply by x1 of s. So I have to get rid of x1, right? So from this equation number 2, I'm going to solve for x1. So I'll take this guy to the other side of the equation. If I do that, this will be positive. So this will be bs plus k2 times x1 of s. This is equal to m2s squared plus bs plus k2 plus k3, right? Okay, times x2 of s. And then from this, you can solve for x1 of s, which just be equal to m2 s squared plus bs plus k2 plus k3 x2 of s divide by bs plus k2. Now I'm going to take this and substitute in the first equation. Okay, so where there's x1, I'm going to substitute here. Okay, so from the first equation, I have f of s equal to m1 s squared plus bs plus k1 plus k2 times x1 of s. So in place of x1 of s, I'm going to put that, which is m2 s squared plus bs plus k2 plus k3 x2 of s divided by what? This is whole thing over bs plus k2. And then this side has to have something minus, right? This guy here. Where is this? Minus that. Wait, no. This equation. Minus bs times x2. Minus bs plus k2 times x2 of s. Okay, sorry about that. So here I'm going to combine this as a single fraction. I'm going to multiply this by that, right? So just everything just over all that, isn't it? Okay. So f of s, this becomes, okay. If you want, you can start expanding this. I have no time for that, I think. Just be the same thing. Plus bs plus k1 plus k2 times m2 s squared plus bs plus k1 plus k2. Okay, so what I'm going to do, I'm going to factorize since x2 of s is common to both, right? So I'm going to put these brackets here, and then here, since I'm out to write this single fraction, this will be bs plus k2 squared, right? Like this, okay? And then I put x2 of s outside like this, and then this will be over what? The same, which is bs plus k2. Okay, now as you can see, remember the transfer function is simply x2 divided by this, isn't it? Okay, so what I'll do, I'm going to divide this side by both sides by f of s, then here again by f of s, and then at the same time I'll take this side on top and then divide by this whole thing, right? So you notice that if I do that, you're going to have x2 of s over f of s. This is equal to what? Bs to be on top plus k divided by m1 s squared plus bs plus k1 plus k2, okay, and then multiplied by m2 s squared plus bs plus k1. This will be k2 plus k3, right? K2 plus k3, yeah, plus k2 plus k3 minus bs plus k2 squared. So this becomes the overall transfer function. You can do some manipulation and all that, expansion and all that, okay? But I'll just end it here. Okay, so if you're not familiar with the method I've used, I'm going to get another video where I'm going to use the freeboard diagram method, where you have to create the freeboard diagram for these two masses, okay? So I'm going to get another video that is going to look at that, okay? As for now, thank you so much and God bless.